All right, students, so we're talking about growth and decay problems, also half-life, and we're going to look at some specific examples and then deal with, identify what the formula is. So let's get going. So let's say you've got an amount of something. It could be money, could be stores, could be bacteria or whatever, and it increases each year by 25%. And maybe the original amount was 200 units, $200 or whatever. So if it increases 25% each year, then another way of thinking of that is at the end of the year, you have 125% of the amount that you had at the beginning of the year. So at the end of year 1, you would have 200 times 1.25. At the end of year 2, you would have 200 times 1.25 times 1.25, because at the end of year 2, or rather at the beginning of year 2, you would have the amount that you had at the end of year 1. So you would have this amount, and we're going to take that amount and multiply it by 1.25. So we can simplify that to say it's 200 times 1.25 squared. At the end of year 3, you're going to have whatever you had at the beginning of year 3 times, and again, 1.25. which when we combine those, you have 1.25 cubed. So you can see that at the end of year t, you would have 200 times 1.25 t. And this is if you are adding a specific percentage at the end of each year. Previous videos, we kind of talked about the same sort of situation. Instead of saying it increases by an amount, or whatever, we normally said it would be compounded or whatever. And that also dealt with situations where maybe you were compounding it, well, sometimes continuously or semi-annually or quarterly. We're just looking at the annual, the once a year sort of situation here. So generically, if it increases r% per year, then your final amount, A, is equal to P plus 1 plus R to the T. This is, we can see a special case where of the A plus 1, A equals P plus 1 plus R over N times, or to the power N times T, but this is just where N is equal to 1. If you had a situation where it was decreasing by r% per year, then that plus right there in the middle would turn into a minus. Okay, so let's talk about half-life for a little bit. So half-life, if a certain substance has a half-life of 100 years, what that means is that after 100 years, half of it will remain. The other half will have deteriorated in some way, maybe turned into energy or evaporated or who knows what. So let's say you have originally 30 kilograms of a substance. After 100 years, you would have 15 kilograms remaining. The other 15 kilograms would have gone off to dissipated somehow. After 200 years from that starting point, you would have half again of what you had there. So you don't lose. It's not like it's all gone in double the half-life. It's just you drop down to 7.5 after the next 100 years, and then 300 years from your starting point, you have 3.75 kilograms. So part of the idea is it never completely goes away. It's always there a little bit, but just diminishing by half every 100 years. So that kind of gives you an idea about what's going on. If we think about it mathematically, we would write after 100 years it would be 30 kilograms times 0.5. Then after 200 years, it would be that amount, 30 times 0.5 times 0.5, which we could write as 30 times 0.5 squared. And then at the end of that third half-life period, so after 300 years, we would have what was left here, the 30 times 0.5 squared. That squared right there is incorrect. It should be right above the 5, not around on the parentheses. That's a typo right there. So it would be that amount times 0.5, which we could write as 30 times 0.5 cubed. This is correct. So thinking about this more generically, it's decreasing by 50% per half-life. That is per half-life period. So that gives us the formula A equals P times 0.5 T. It's just once again, it's a special case of something that is decreasing every year. at 50% half-life just means 50% decrease. So if we took that previous formula, we could say 1 minus 0.5, and that would give us 0.5 inside the parentheses. So you don't necessarily really need this as a separate formula, but it's kind of helpful to have that for a quick reference. The other type of thing we'll see here in the next video are some problems where they'll use the phrase there is a continuous exponential growth model. And all that means is, what we've seen as related to previous videos, is that something is being compounded continuously, which corresponds to the formula A equals P e to the RT, where R is a percentage and T is the time period. Specifically, R is the percentage of growth over whatever your time period is. So it might be it is growing at, is being compounded, 3% per that time period, and that time period could be per second, per a given number of seconds, or a given time period like weeks or days or whatever. And then this is going to be the number of time periods. And then down here you can see if it's a decay, so this is also known as an exponential decay model here, you're going to have a minus sign right there. So in reverse order, this is exponential growth and decay, half-life, as well as just annual growth and decay. Thanks for watching.